Hello, everybody, and welcome to the 50th episode of the Hyperthesis Podcast. My name is Liam.
My name is Feely.
And I'm Patrick.
So today we've got some interesting things to talk about, from tsunamis to units of measurement. So I'll start us off with the intro topic, which is on tsunamis. I want to talk about tsunamis a little bit and a paper I read regarding them. So tsunamis, they're these really destructive waves, which you've probably heard about or seen in movies or TV, and they cause these massive losses of life and destroy coastal towns and cities, communities. And that's the part of tsunami that, what I guess if you ask the average person what is a tsunami, that's what they think about. They think about this massive wave just leveling a coastline. But there's a lot more to them than that, it turns out. So long before tsunamis reach the coast, there are these long waves in surface waves in the ocean.
Well, I put a little note for the tsunamis too. I think before 2004, it wasn't really a thing. People don't know it that well. I remember, because I was really young, but I remember 2004 Indian Ocean tsunamis where it hit the coast of southern Thailand, India, and other place, and nobody had any idea. Few people had have some idea of that. Oh, there's tsunamis that happen. What if the water goes down really quickly, and it's like, oh well, it's all good, and then they get swept, right? A lot of people lost their lives. I remember watching the televised report and news. It was devastating. And after that 2004, almost everyone put an effort to put in this kind of tsunami detector in the deep ocean and far out to really have like an entire new system of warning that comes on for tsunamis and really raise awareness of this, in a way not new, but because it has probably hadn't happened for a long time, kind of forgotten. And yeah, that was quite experience. There was so many unmarked what's called bodies, and I think to this day some of those were never identified. It's kind of crazy because I think 2004, even though we had a lot of technology, is still not as good as now, right? But yeah, tsunamis are actually very devastating.
Yeah, and they're really hard to predict, that's a lot of the problem behind them. And I think there's a lot more tech, like you said, when a tsunami hit, humans have this thing where we tend to we ignore problems until they affect us a lot, and then we really jump on top of them and try and fix them. So we probably have a lot better technology now after some of these more disastrous tsunami events.
Well, a lot of big tsunamis come from also earthquakes under the sea, or like these kind of like volcanoes under the ocean, right? At the sea floor happens, and every time they detect like large earthquakes, they always talk about the possibility of the tsunami hitting the coast. That's why they have all these probes around. Even though we might not be able to predict it, but we are able to detect early signs of tsunamis. That's good, right? So if we kind of, I believe I'm probably gonna explain how the wave work here, but like you can detect certain signs of the tsunami through specific waves of type and the behavior, even in the middle of the ocean where it doesn't seem like high at all. I think Liam gonna talk about how it's compressed and becomes large wave, but in the middle of the ocean is really flat, right? It looks like there's nothing going on. But we are able to detect those signs that be able to warn people that tsunami is gonna happen. But even though we have no way to stop it, unlike in the TV series The Flash, somehow he stopped it, which is hilarious. But
Okay, I didn't watch that, but yeah,
me neither.
tsunamis in the open ocean, they're a lot less scary. It's when they reach the shore they get scary, and there's the mathematical theory that describes them. It's called gravity waves. Not gravitational waves like we've talked about before, but um, waves that occur in the ocean. And they kind of their overall kind of size and wavelength is determined by the acceleration due to gravity and the depth of the water and some other things. Um, But so in the open ocean, so like earthquakes and volcanoes and things, they vibrate, they cause the earth to shake, and they'll create these kind of waves in the ocean. And these waves, um, sometimes there's other ways tsunamis can form. I'm not sure, but there are these very long wavelength waves that travel on the surface of the ocean, and they can propagate very far from an underwater source at a very fast speed. So in the open ocean, they move at about 700 kilometers per hour, which is quite fast. So, for example, a tsunami could form on one side of the Pacific Ocean, and it could reach the other side, so the North American side, in less than a day. And this is something that's happened before. So, for example, there's like earthquakes in Japan, and these large wavelength waves can reach over to North America like within a day. And there's models, like simulations and models I've seen of kind of pictures of the Earth from space and what they look like, and it's very interesting. But if you're in the middle of the ocean, these waves aren't very tall. They're kind of um, the waves rarely are more than a meter tall. So if you're in a boat in the middle of the ocean, you don't really even notice this wave. It kind of just passes through you, and maybe your boat moves up and down a little bit. Um, but as they approach the shore, that's where the kind of destruction occurs. And like you said, as the depth of the water gets shallower and shallower, what happens is that the wavelength becomes smaller and smaller, and the amplitude of the wave gets larger and larger, and its speed slows down. That's what you say when the tsunami approaches the shore. You see all this water the water recedes a bunch, and you see this very slow moving large wave form. So it could seem like a very long time for this wave to eventually hit the shore because it just dramatically slows down to what feels kind of like a standstill sometimes, although it is still moving. But and then it gets much larger because of this kind of physics that changes its amplitude.
There's this story about this kid, like who were playing in the ocean with a lot of people, right? And when the tsunami happened, he noticed that the water goes down rapidly, and everybody is excited. Oh, what's going on already? But he knew, or thought he knew, right? So he just screamed tsunamis, tsunamis, and he's actually little kids saved a lot of lives because no other people they didn't know. Apparently, like the people who know, holy smoke, right? And the kid saved a lot of lives. So if you know that stuff, it's something that everybody should be trained to when you go to the
Mm-hmm.
ocean. In a way, right? You should learn that in science class. I remember having it's like a model top thing that teach everybody that when you go shallower and the wave kind of the amplitude or the height of the wave gotta like explode basically. Yeah.
Even when you're at like the beach and there's regular ocean waves hitting the shore, you normally you notice how they approach the shore is when they get big, right? You don't see these big waves coming from far away, and when they reach the shore, you can see them bump up a bit more. So it's the same kind of physics. It's just tsunami waves are quite big, and then so when they reach the shore, they're amplified a lot more, and they can go really far into the shore. They can go as far as 16 kilometers inland, depending on the various conditions. So yeah, if this kid, man, what a trooper! Like I feel like everyone should be taught this, depending where they live in the world. I guess if you're in the middle of like a continent, maybe you don't need to know that as much. But anyway, so that's kind of like the basic idea of a tsunami. And I read this paper by Sir Michael Berry, so he's a kind of famous physicist, and he has a lot to do. A lot of his research focuses, funnily enough, on focusing events. Um, And it turns out that the same physics which describes rainbows and tidal bores and classical turning points in quantum mechanics, it also describes tsunamis. And he wrote this paper on it. I'm talking about how tsunamis, and he's only talking about the open ocean part, not when they're near the shore. When they're near the shore, there's a bunch of funny physics happening. But when they're in the open ocean, you, they look like what's called an Airy function. And I've talked about this thing called catastrophe theory and caustics before, so it's funny how it all kind of comes back in all these scenarios. But that's not what I wanted to talk about. I want to talk about the focusing of tsunamis, not kind of what a tsunami looks like. I don't want to talk about what a bear tsunami looks like. I want to talk about how tsunamis can be focused to be even more devastating. It's just like imagine you have glasses, right? You have a lens, light goes into it and focuses. You can create lenses for sound waves and water waves and all kinds of stuff like that. So it was this 2007 paper published in the Proceedings of the Royal Society A, which is some physics journal. Um, and he found that these open ocean tsunamis, so long before they hit the shore, they can actually be focused by underwater islands. And by underwater island, I mean like imagine a mountain on the bottom of the seafloor, but it's underwater. And what happens is that as these waves travel over this underwater mountain, so there's surface waves on the ocean, but there's a change in depth of water underneath them. Just like how when the tsunami approaches a shore and the change in depth causes them to change their properties and get bigger and different wavelengths and slow down, you get something similar happening from these kind of underwater mountains. As the tsunami passes over it, it actually acts like a lens, like for light, and it focuses the tsunami into this kind of cusp shape. So you can actually increase the destructive power of the tsunami by a lot, just because it's passing over these underwater islands that act like a lens. Um, and actually, the cusp shape, the cover art of our podcast is this thing called a cusp catastrophe or a Pearcey function. It's these little focusing events from light. Like imagine you have a wine glass and the sun's shining through it. You get all these fun-looking water shapes coming out the other side, or even those wavy lines at the bottom of swimming pools. The kind of same physics that describes how these tsunamis focus due to these underwater lenses. So it's a lot of details on sweeping under the rug, but in essence, they're the same. They're this universal phenomena. So I thought that was kind of neat, but it's also imagine you get one of these earthquakes on one side of the ocean and these waves travel across the ocean to the other continent. There's a lot of underwater elevations and depressions everywhere, so you're going to get a lot of focusing of these waves, especially closer to the shore. So it might be worthwhile to kind of like map out these more significant underwater islands because you can actually predict kind of like hot spots where really large tsunamis would hit. So for example, if there's no underwater islands, tsunami might get really big and nail a shore and cause a lot of damage. But if there's if there's the kind of like the perfect storm of underwater islands, you could get a really, really big focusing of the tsunami, and you can even get like I forget how it scales, but it can really increase the amplitude of these tsunamis when they hit the shore to be even more destructive than like your average tsunami, which is kind of scary to think about actually.
It's very interesting to me that this would cause a focusing event because I remember learning about different types of waves in the atmosphere that are produced when you have wind, like a very steady wind blowing over a mountain, and that kind of projects it upwards, but then the waves spread out almost as if it's like a point source. So it's very interesting that this is kind of doing the opposite effect with this tsunami wave, where you have this plane wave coming in, interacting with this underwater mountain, and it's being focused, whereas in the atmosphere, those types of waves, plane wave, or it's not necessarily a wave to start with, but it's a constant wind that's projected up into the atmosphere and spreads out.
In his model, he actually didn't model the incoming waves as plane waves. He modeled them as spherical waves as well. And I think that might have been a big part of it. Because even if you have plane waves, you should get a caustic, so you should get this cusp shape. But I'm not sure how it changes. The plane wave is like the far field limit of a spherical wave. So imagine like a spherical wave is like you drop a stone into a pond and you get this little like ripple comes out as a circle from it. A plane wave is like if you've ever been at the beach and you see this one straight line, like a wave that looks like just a straight line coming at you. A plane wave is kind of like if you let a circular wave go on long enough, it looks like a plane wave. So I'm not sure the difference that his model had, but I think these wavelengths, these tsunami waves, they're such long wavelengths that you actually probably need to take into account the fact that they're spherical waves in the ocean. Making a plane wave, it might not give you the full physics, or making a plane wave approximation might give you bad physics, although it's probably decent, but I'm not sure. But my immediate thought was that okay, these underwater islands act like lenses. They create some index of refraction, but for water waves, so they act like lenses for light, and they focus this. What if you had an underwater hole? So an anti-depression, I guess you could call it, or like an underwater pit. So imagine you have this ocean and it has this constant depth everywhere, but suddenly it just gets really deeper for one specific point. you might guess that it would act like a defocusing lens. So instead of a lens that focuses light, it acts like they call it a convex lens or a concave lens. I can't remember which one's which, but you think it would disperse these waves instead of focusing them. But it turns out that's not the case. Actually, this anti-focusing hole, it creates two focuses instead of one big one in the middle. It kind of creates two smaller ones on either side of it, and that's something I was trying to look into a little bit. Actually, I'm not sure exactly why. It might be because of the fact that waves in the ocean have a nonlinear dispersion relationship, so they're not linear, which is just a fancy way of saying their speed changes depending on the situation. But maybe we shouldn't get into that too much. I just thought it was very interesting that you can get this focusing stuff.
Well, few things in life are linear, but we can use linear like a way. We have very good way in science to linearize them, right? Like or put things as linear to make it seems linear or approximately linear.
Yeah, the whole reason I want to talk about this is, well, we talked about gravitational waves, and I'll try and speed through this for time's sake, but we talked about gravitational waves a lot in some of the previous episodes this season, and even before that. But at my conference in Italy that I went to, there was this big name in my field of analog gravity who was there, Silke Weinfurter, and I came up with this idea for Duncan. My supervisor, I was talking to my supervisor about how, like, Duncan, like, gravitational waves are like any other wave. So if they pass through like a neutron star or a planet or even around a black hole, they'll focus. You'll get a caustic. You'll get this cusp shape that looks like the image of our cover art for this our podcast, right? Because it's this universal stuff. And I was like, so what if you could kind of basically use neutron stars to get stronger signals for your gravitational wave detectors, or even like black holes or planets, right? And he was like, oh, that's kind of neat, but he didn't think too much of it. And then I went and found this paper that this big name in my field published a year prior to that. So she beat me to the idea by like probably 4 or 5 years. But, well, the paper was published a year after I had the idea, but they probably been working on it for a while. So she co-authored this paper called Wave Focusing by Submerged Islands and Gravitational Analogs, where she built upon this Michael Berry idea that these underwater islands act as focusing events, and she showed that it's an analogous system to neutron stars focusing gravitational waves. The mathematics of them is the same, except instead of water waves or tsunamis, it's these ripples in space-time, these gravitational waves. So it turns out stars like our sun or even these neutron stars, they have the exact same effect. They act as a lens for gravitational waves, similar to how a black hole acts like a lens for rays of light passing around it. So yeah, I just thought it was kind of neat that I had an actual idea for like an actual. It's not a unique idea because someone beat me to it, but it was almost a unique idea. As far as ideas come in physics, most of them have been done many, many years ago, and this one had only been done a few years ago. So I was quite proud of that, actually, even if someone else had done it.
Well, one could claim that a lot of things we discuss about in like psychology or sociology have been widely explored by the Greeks, but
Yeah,
we'll see.
Yeah, fair enough, I guess, but I don't know enough to comment on that. But anyway, that was my little introduction to tsunamis and a nice little connection to gravitational waves. But today, that's not our main topic. Our main topic will be led by Feely, and it'll be about how unit and measurement affect our scientific understanding. And this comes from, we had an episode where we talked a little bit about this stuff, and we got an Instagram message from Mr. Plow or Mr. Snowplow asking us to talk more about this subject because he found it very interesting. So, Mr. Plow, this one's for you, my man.
Well, so this is gonna be more, I think, fluid and yes, spontaneous type because I want to really bring out our experience on basically measurement and what we think really in science why or even not even why what it's like to have this type of measurement process or this unit system because people in different part of the world they came up with all different types of units of measurement, not even just in space, and not just length, there's time, the tones in music, and you can find all these like very a variety of plethora of systems that exist around the world and actually help shape our understanding of the world really. And I want to compare it to language. It's kind of strange comparison, but a person who speaks certain language, I mean, it defines your thought, right? Well, I think I put this quote up before. It's like um, what's it called? Your native tongue is your true motherland. They're kind of strange because there you could be a language that doesn't have directions, or or everything is based on northwest and people would think different way. And I think it's similar way to how we think as units. Like in North America, people use like pounds, right? Like for weight a lot. And when you say, oh, how are you like 200 pounds something, to me growing up in kilograms, I was like, "Ah, that doesn't really mean much." Right? I had to do conversion, in my head, or like miles, for example. Even the British, they use stones, right? Like, so the idea of units of measurement has been, I think, very important. But however, in science, we use the metric system a lot, or we have the SI unit, right? Where it's basically standardized around the scientific community that we talk about. So we really have to agree on what we call the fundamental unit of things. Let's say, SI unit, we have like seconds, coulombs, meters. But in a way, those units are defined for like as per human. So when we put something as a definite, right? If we put something, well, you want to measure something, you have to basically limit it or define it. So people, I think, has been used or have used like body parts to define length for a long time. And as for time, the obvious reference is the sun and the moon. So a lot of the artifact or the relic of the past that came along with time, coming like sundial as a clock, and the fact that I think we talked about before that the second or minutes, why is it 60, come from, there are all these systems that has been thought about throughout history to basically define specific unit length or unit size.
Yeah, I think it's interesting how these are defined, and even something like the metric system is somewhat arbitrary. Like, I know the metric system is based on the meter, hence metric meter. But it was based on the fact that a meter was classified as it was 1/10,000th the distance between the equator and the pole of the Earth as it ran through Paris, which is pretty arbitrary, to be honest. It's not quite the same as like, oh, a foot is the size of my foot as a king, but it's still, I mean, it's dependent on the size of the Earth, and even then those calculations were not as precise as we have today.
Well, in scientific community, we kind of move to use at least for theory people, right? We use natural units a lot where, we know certain things that are absolutes. And, some people could debate about it if it's actual absolutes, like, speed of light, for example, that you can literally classify or like start all the entire units of system based on just specific constants that we know is absolute. Like speed of light, we have the Planck's constant, and those stuff. The combination of those define our units really. So instead of saying I'm going 10 meters per second, which in a way for us human makes so much sense, you could say I'm going, I don't know, like 1/1 millionth of the speed of light. So in a way, even though it's a relative scale, but since we know exactly that the speed of light is fixed in vacuum, it's just one speed that never change, allegedly. So we just divide relative to that, right? And if you look at units of weight, for example, like 1 kilogram, that's like a bar of mass somewhere in the world where we all agree on as a community, as humanity, that is 1 kilogram, right? Even and they have to very very careful of like the way to maintain it, make sure like it's no contaminants or things, and we agree as 1 kilograms, but also we can also base mass upon speed of light. So we are kind of so define unit of measurement of weight in a way, or mass, as the speed of light.
Yeah, you got to be careful with those physical definitions, though, like you said, right? Because even like the elements that make up this 1 kilogram, they decay over time, so its mass changes a tiny amount, and crazy stuff like that. Um, there's a really good, I'm trying to find it right now on YouTube. Yeah, there's a pretty recent 7 months ago Veritasium video actually. It's called "The World Depends on a Collection of Strange Items" or something like that, and it talks about like how the standards, and maybe this isn't quite units of measurement, but it's like it's the same idea, is that somewhere in some warehouse somewhere in the world they have like a jar of peanut butter, and this peanut butter is like the world standard for like what is peanut butter, or maybe it's like North America's standard, or I don't know how global it is, but all the peanut butter factories that make peanut butter, they get like in this warehouse they make the most pure peanut butter that they can, and then that becomes the standard. And then everyone else says that, like, all right, when we make peanut butter, it's based on this stuff. And it's kind of the same idea with these physical things, like, what is a meter? It's like, well, we have the meter stick, the perfect meter stick. That is what a meter is defined by. For example, if you had a physical meter stick, but I don't know, nothing's perfect, right? So you got to be careful with these.
Yeah, and I think that's a use of the metric system, and for example, using the speed of light, is the fact that none of these values are, well, I guess the second kind of is, but none of these values are defined on physical objects anymore, because the speed of light is defined as, or a meter is defined based on the speed of light. A kilogram is defined the speed of light, Planck's constant, and a couple other variables, which before had been uncertain, but now they've cemented them down. Primarily Planck's constant, which now has a definite value and is used in the calculation of a kilogram. So beforehand, we used to have these very heavy, 1 kilogram masses that were used as the standard. So if their mass changed at all, that was still a kilogram. Whereas now we've defined the kilogram based off of these, I guess, more natural values. And even a second, which was previously had many different definitions, but for example, was defined as the time it takes for a solar day, or 1 divided by 86,400. So the time that it takes to do a solar day. So, and now it's based on cesium, which is a lot more concrete because we know the Earth's rotation is going slower. So it's very interesting that we've moved away from these physical objects, although the object warehouse where all these standards are produced is really cool. We don't have those physical standards anymore for the metric system.
Well, the thing about standards is like, it doesn't necessarily the most pure in a way. Like, like it's probably not the best tasting peanut butter, right? But the point of definitions is to be precise and as to classify things, right? Like to separate one another. So you want to find the essence of what makes it be peanut butter, right? So it might not be the best peanut butter you ever taste, but what it essentially means is like, oh, we can make the equivalent of butter out of peanut, and that process, and what would become the elements, or like the combination of elements that come out of it. So we can for sure can define the word, or like the item called peanut butter, and that the essence of peanut butter, even though the commercial peanut butter, there's a lot of things adding to it, right?
Yeah, and it's very interesting to see the standards that we have established. Like there's a whole organization dedicated to these weights and these different standards. So one of them is the International Bureau of Weights and Measures, which is based in France, and they're kind of responsible for defining these different values. But even there's defined standards for producing a cup of tea. Going back to YouTube videos, there's a Tom Scott video that discusses the standard for making a standard cup of tea. And the use of these standards is particularly important in science because they're repeatable, which in science is pretty much everything, unless you're doing theory.
Well, and also like, I remember vividly, we talked about photography a few episodes ago, and they also have like standardization too. In fact, the thing called ISO, right, is International Standardization Organization, if I remember correctly. So it basically defines or shows like the sensitivity of your sensor to light, and the number would be like 100, 200, 800, 1600 up, in the multiples of 2 from there. And they're interesting, right? Like, because in a way, for a person who don't do photography, or even people who do photography, also see that it's like arbitrary. It doesn't really come with a unit. So in a way, if you look at other things like shutter speed is in seconds, right? Even like the f-stop is an index, but they also have like a geometrical value to it that correspond to certain things, right? But the ISO is basically just some arbitrary standard. It's based on specific criteria, of course. But what the point I want to make is there are a lot of arbitrary stuff that we just accept as human beings, or even as scientists, as students, as anyone who live on this earth, that we really just intuitively accept those standards as normal, even though some of them are relatable, like length and time measurement. And we also have other measurement even for like gasoline, for example, right? Like the octane of gasoline, those number. And some people just, I mean, you don't really need to understand what they mean, but it's useful sometimes to understand that all numbers without its units are almost meaningless.
Just to mention here, there was also standards used for very abstract ideas, not just measurements, but for example, currencies. The gold standard was used for quite some time. I think like late 1800s to early 1900s, in which essentially the US dollar especially was directly connected to the price of gold. So if the price of gold went up, so too did the value of the US dollar. And essentially they could be exchanged 1 for 1 to whatever it was. But this was a way of kind of standardizing currency. Of course, now a lot of the world's economy, bar a few countries, is based on the US dollar, so it's even a bit more abstract. But this desire for standardization and basing these measurements off of kind of arbitrary values, I guess, is in practice everywhere in everyday life.
Well, the other thing I want to point out is our music and tones too, because the measurement of tones has been actually very different around the world. I think because the classical era was so prominent in the Western world, everything kind of got standardized from there. But if you go to more Eastern, like the Middle East has their own thing. They actually have a bunch of instruments with what we would call it microtones, where they have a lot of like sound in between, let's say A and B notes, that people you can see like they're similar to guitar, but have so many different frets. Like it's just insane. Even in my country, we have our own tones and system that we devise for it, and our let's say our A5 is not the same as Western A5. Even the Western itself, right? Like the Baroque era is usually lower. So it's not the 440 hertz was chosen specifically to, I think, from scientific community, but at the time back then it wasn't really accepted because people didn't tune it to 440. I don't tune my guitar to 440. I tune it to 432. But Liam would know more. Like bagpipes I don't think they tune to 440 either. Like I think bagpipes tune very relatively. I think you have to tune it every time you play it, or like mid play, right? I noticed that too.
Yeah, I played piano for a long time, and pianos were very nice because you just like paid someone to come tune them every like few months or something. Or if you were like me, like once a year, because I wasn't super serious about it. I just did it for fun. But bagpipes are very finicky. You got to tune them like the air pressure changes, or a cloud goes over the sun, or Mercury's in retrograde. Like, it's too many degrees of freedom in a bagpipe to control very well. So it's like an art. Like a very good player is very skilled in controlling these degrees of freedom, and they know what to do and when to do. But yeah, I think like bagpipes, different bands, different soloists, they tune at different frequencies, and we're very sharp compared to like concert pitch or like 440. I think like my band right now, like I think we tune at 482 or 480, and it like changes. Like if it's a hot day, you go up to like 486 sometimes, or even higher, hertz. But one thing, yeah, that's pretty sharp. It's pretty. There's also this interesting effect talking about how everything's relative, right? Like if a band goes out and they're tuned at 480, and then the next band goes out and they're tuned at 482, even though they both bands could be perfectly in tune to the 480 and 482. The 482 one sounds brighter because it's sharper, so it sounds like more good. It sounds better essentially. So there's this kind of like there's this effect. You got to be careful, but that's kind of a side conversation. We talked about this what you mentioned, Feely, about how different cultures kind of have defined different scales and different like pitches and tones and things. We talked about that in our music episode a long time ago, a little bit actually. You talked about it, I think.
Well, the next thing I kind of want to touch on is on measurement, because for anyone who has done quantum mechanics, measurement is such a big part. I think we talked extensively about it in previous episode at some point. But the fact that we understand know about the Heisenberg uncertainty principle, where now we kind of understand that, well, wait a minute, when we define something, there's always an error associated with it. Even in the smallest scale, that the length, we say 1 meter, but it's not really 1 meter, isn't it? It's 1 meter with an margin of error that can be very, very small. That's what's the point of maintaining this, all these objects or something, because it's a reference point where at least we can control, let's say, you know, um, you have 1 kilograms, but every day if it fluctuates by 10 grams, that's a lot, right? Like then what is 1 kilograms? However, if we can control it really well, where it's, let's say, like 0.00001% fluctuations per day, that's like maybe that's pretty good, right? So every value you see, every scientific constant you see are not complete unless they specify the errors, or like the you usually see it as a plus minus or something. And some people would say, oh, 1% is good enough. But like if you're doing precise measurement or precise instrumentation, 1% can change the entire outcome. Especially people who work with like chaotic systems, like 1% is a lot. It changes the solution entirely. If let's say the course of the a star ship, spaceship or something was moved by 1 meter, it's like, well, we might end up in another part of the universe and try entirely. Who knows, right? If that ship goes on for like the next million years. So there is the measurement uncertainty is so important, incredibly important in scientific communities. Basically, if you publish any experimental result without uncertainty, it's basically nobody will accept it.
Yeah, because you're limited. I mean, everything you just said, right? You're limited by your tools and all that stuff. And I guess if you're doing like quantum mechanics research, you're also limited by that, like you said. But yeah, that's exactly in first year physics labs. That's like the thing they really hammer into your brain is that you have to think about uncertainties. And I've moved on to be a theorist, and I never think about them. But when I'm TAing first year labs, it's like everything you do, you have to put in like how certain are you, and a lot of the time there's math to it. There's like actual like rigorous mathematical ways to deal with uncertainty, and it involves calculus and things like that. But a lot of the time it's more so you just have to have like intuitive guesses in your first year physics labs. You say like, all right, I have a meter stick, how accurate can I measure this thing? And you say like, all right, it's plus or minus like, I don't know, like a millimeter or 2 millimeters or something like that. It depends on what you're measuring and what you're measuring it with.
And students hate it. I like a lot of students hate doing uncertainties. I understand why too. Like, and there's theory uncertainty. If you don't have a good conceptual grasp, not even mathematical, like conceptual grasp of what calculus does, you really struggle to understand uncertainty. But once you understand how, like, derivatives or differentiation works, and why what is rate of change, and why would uncertainty be affected by rate of change, it really clear up your understanding of uncertainty principles, or like how to deal with uncertainties. Why do you need to combine uncertainty this way? And without calculus, you can have like intuitive understanding of it, but with calculus, the clarity is just much, much better.
From an experimental perspective from this, I mean, a lot of experiments, their aim is to just reduce uncertainty. Like from my master's degree, I was working with experimental systems, and there was a high uncertainty because of leaks in the system, for example. And so everything that we do, we try and limit uncertainty to get the best data possible. And in a field like particle physics, you're trying to eliminate the uncertainty enough that you're positive about an answer. So, for example, with something like the discovery of the Higgs boson, they make sure that they're 5 sigma, which has to do with the uncertainty of the answer. But it's within 5 sigma, so that means that they're pretty much like 99.99 something percent sure that the Higgs boson exists, and it's not just a random coincidence that its decay products were produced in the Large Hadron Collider. And so a lot of experimental work and a lot of effort that goes into it is reducing uncertainty in the measurement, and then also figuring out how to take those measurements in the best way possible. So using better tools or better analytics or even just more data, because if you make a measurement once, you have a higher uncertainty than if you make that same measurement 100 times using the same instrument.
Yeah, that's something you also hammer into a lot of first year physics students' heads, is that like the analogy I tell them is that if you go on Amazon, right, you don't buy the product with a single review that's 5 stars. You buy a product with 2,000 reviews and an average of 4.5 stars. Even though it's less than the 5 stars overall, you have a lot more kind of, what's the phrasing? You have a lot more certainty in the measurement because you've taken so many of them, I guess. But one thing I wanted to quickly come back to, Felix, you said, also coming back to first year physics, you said that no number, or I forget how you word it, but basically you need units with your numbers to make sense of them. And that's pretty much something else you always hammer into first year physics students as well, or like even like high school physics, right? Like every time I mark something, like it's always, people will write down like, how fast was this car, and they'll just write like 20. And it's like 20 what? Like 20 feet per second, 20 meters per second, 20 kilometers per hour. So you need units to make sense of things, but there are a lot of numbers you don't need units for, and but those are ratios of numbers with units. So ratios are another powerful thing in physics. That can tell you a lot about a system.
Well, people used to used to think that ratios were more real, because like everything's made of ratios. Where I think that's very Pythagorean thinking back in the days. But also, it's a good practice to put down your units in your calculation, especially when you're unfamiliar with the equation. Because like I always tell my students, if we're helping them, it's like, well, when you write down this calculation, you never put units down, and at the end you get some number, and you don't know if that number makes sense, or you did some calculation wrong, or maybe you divide wrong some point, right? But if let's say A times B times C divided by D, instead of writing 2 times 5 times 7 divided by 8, you have to write like 2 centimeters times 3 seconds divided by, like if you actually explicitly write them down, it's actually like super helpful. And sometimes you find out that your mistake is you're putting the wrong units in. They don't cancel out, or they don't combine into the units that you want. And I think it's an excellent practice that that like really good students if they do that, you realize like they actually thought about it instead of trying to just calculate and go.
A remarkable amount of progress in physics was actually made by dimensional analysis, which is just a fancy way of saying people knew about units or things like that. So you get these so-called back of the envelope calculations where you say like, all right, like I have you just you have these types of units and you want your output to be some type of unit, so you just plug things in and you get like a physical constant out of it. And I don't have a good example off the top of my head, but
Well,
we've seen
I
it
do.
again and again and again in physics. And yeah, you have an example.
Well, my example is quite technical, but when you do statistical mechanics, you want to basically combine the classical and quantum realm. Because when you compute a partition function for basically classical magnetic system or some system, the units don't really work out. So there must be some prefactor onto the partition function that somehow fix this. So we kind of knew from the commutators in quantum mechanics that if you do position and momentum, h bar comes up at some point, right? That's the artifact or the nature of quantum mechanics. But if somehow actually if you put this 1 over I think HQ into as a prefactor, everything works fine. And there are mathematical reasons for that and whatnot. But there are methods that even though we can develop formal development to figure this out, it's a very good guidelines as to what should be in terms of units.
I think it's interesting at this point to introduce the idea of natural units. So we kind of mention them, but natural units are essentially units of measurements which are defined based on the physical constants, like the speed of light or the Planck constant, and they're arranged in such a way such that they have a numerical value of 1. And so these natural units are able to be expressed without the influence of, say, arbitrarily picking the distance between the Earth's equator and North Pole, instead setting these universal constants as 1 and then basing everything else off of them.
Well, these are basically ratios that Liam talked about, right? Instead of talking thing in an absolute term, we know that absolutes there are only certain things that we know are absolutes. So we base everything else, everything of measurement on those absolutes as ratios of those absolutes.
Yeah, natural units are an interesting thing. I have mixed opinions about them as someone who has to deal with them a lot. Because in quantum field theory, what the physicists do is that your math is pretty complicated. So you use natural units to make it look nicer. So for example, E equals mc squared is this Einstein's famous equation. In natural units, it's just E equals m. You let C equal 1. So the units of your energy end up being the same as units of mass. And you get some crazy things. I'm trying to remember some ridiculous ones, but you get like silly things like that, for example, or your units of momentum are the same as your units of energy. But it all works out in the end, because in the end, you do all your math, you set all these things like Planck's constant and C to 1, you ignore them. And in the end, you know that whatever calculation you did, the output has to have some units. So you just kind of arbitrarily plug in these constants back such that you get the right units out of it. And it works super well. But it's tricky sometimes.
One could say those equations in natural units are the more true form of the equation, because they're not limited by these measurements of the absolutes, right? Like we just call them, everything is in the relative term to the absolute of the universe. Well, there might be debates if they're actual absolutes, right? But in a way, it's a purer form of the equations or the description. And the fact that we add these constants back is because it's our inability to deal with the, to measure like exact things that are exact. We have uncertainties, we have instrumentations, but the law, let's say, if equation in physics are like laws or physical laws, right? In a way that's more true to describe it without the artifacts of measurement, which is like C, for example, that we had to measure, because we know it's absolute. There's a maximum somewhere, but we can describe the behavior of the system without relying on human kind of flawed measurement process.
Yeah, well, for natural units, you need those constants. You need them. You put them back in the end, right? You can't ignore the fact these constants are there because energy and mass are not the same thing. But it's a very useful tool, and it's nice sometimes. I guess it's like all these different units. But anyway, we should.
Yeah. In the description, even though you say it's not the same thing, well, really, is it not? Right? Like there are. Oh, if the physical law states that way, it might be the same thing. We just look at it a different way. There are, I think, debates about that too. So
Yeah,
I think
well,
we're running out of time.
yeah, I guess they're the same thing, just with different units. You know. But yeah, so that's. I feel like this is something we could talk about for so long because we've talked about it before, and we could probably go on about for another hour. But for the sake of time, we should probably move on to our story. So thank you for that, Feely. But before we talk about that story, which we'll talk about some of the mismeasurements in history. So maybe some people forgot their error calculations. Who knows? But Patrick will tell you how you can reach us and stay up to date on our news and all that fun stuff.
Yes. So, if you want to talk about measurements, or you're an experimentalist or a theoretician who hates measurements and dealing with error, feel free to contact us through our many different ways of contacting us. You can reach out to us over email. We are hyperthesispodcast@gmail.com. So you can send comments, concerns, questions, or if you're interested in being on the show, we are more than happy to have you. We have a couple guests lined up over the next little while, so we're looking forward to that. And we are always looking for more. You can also find us on Instagram. We are at the Hyperthesis. And so you can leave a comment, follow us. We'll probably follow you back. I don't know how Instagram works. I'm not in charge of that account. But you can check out our Instagram for updates, and you can also send us a message. We are on YouTube. We are a little bit behind on our YouTube, but that's okay. You can still check out previous episodes of the Hyperthesis there, and you can share us with any of your friends or not friends, whoever you would like. You can also give us a like on our YouTube videos, give us a subscribe, or leave a comment. Finally, we are found on pretty much every podcasting service there is, including Apple Podcast, Google Podcast, Amazon Music, and Audible, and we're based out of Spotify. So feel free to contact us, leave a review, a like, a subscribe, a follow, whatever you need to do. And if you have topics you would like to suggest, feel free to send us a message as well.
All right, thank you for that. And, well, I'm handing it back to you for the story.
Well, thank you, sir. So, as Liam said, today's story will be on some notable mismeasurements. So we just spent the main topic talking about measurements and error and how it's very important to include those within whatever you're doing, whether you're fitting a pipe or doing some plumbing in your house or working on high energy particle accelerators. Measurements are important no matter where you go. And something very important, which you might learn in woodworking or metalworking, is measure twice, cut once. Just so you don't cut too short or too long. And you definitely don't want to cut things too short, especially if you're building shelves in your house. So there have been a couple larger mix-ups than just accidentally cutting a piece of wood too short for your shelving or having 100 feet too long of plumbing tubing, and I'm going to talk about a couple notable ones. The first, which is not too severe, but was quite costly of a incident, and this happened in France in the early 2000s. And so France was looking to order new trains for their rail system. If you've ever been to France or heard of France's rail system, it's quite good. It's very extensive, covers the whole country. Much better than anything we have here in North America. And of course, when you get trains that are used a lot, you need to replace them every so often. And so in France, they ordered trains to a specific size based on their tracks. We won't get into gauge size at all. That's a whole other system of measurement that varies country by country. But the measurements were given by the engineers at French railway company, and they were to be built. Now, these trains arrived, and it found out that the measurements given to the companies making the trains by the French train company were only for platforms that had been built within the past 10 years. Now, France, being a very industrious nation and having been so for quite a while, has a well-established train system, which is much older than 10 years old. And so what they found was that these brand new trains that had been ordered were too big for the platforms that had been built prior to 10 years. And so what would happen is the trains could not fit in the stations with these slightly larger platforms. So during this whole debacle, which was first noticed in 2012, there was a lot of blame passed around, a lot of lawsuits and libel. But essentially what happened was the French government, you can't return these trains. And mind you, there were 1,860 of these trains that were delivered. You can't just return those to the company and say, oh, no, make them smaller. So what the government of France and these railway companies decided was that they would actually expand the platforms by cutting them further away from the tracks to the cost of 50 million euros. So quite an expensive whoopsie that cost a lot of money. But thankfully, the trains do fit on the tracks and in the platform. So they, I believe, are all operational now. But that's a mismeasurement of, oh, we didn't actually get on the ground to check the actual measurement. Something that is very, very important to do when you're measuring anything is to actually take the measurements from whatever you're measuring. Now, I do just want to note that one of the train companies was the Canadian company Bombardier, which is kind of cool. But again, these companies weren't at fault. It was the French rail company. Now, a bit further from Earth and a bit further away from Earth was another instant where it wasn't a miscommunication, but it was an error with the units of measure. And this has happened with the Mars Climate Orbiter. Now, the Mars Climate Orbiter was a weather satellite intended to orbit Mars and relay information about the weather that was going on, so we can study its climate and what was happening. However, it crashed. In 1999, it was lost as it entered the atmosphere, something that orbiters aren't supposed to do or aren't designed to do. They don't have any heat shielding, so entering the atmosphere is catastrophic, leading to the breakup of the probe. This $125 million probe, American, was lost completely, and all the work that went behind it, and an investigation into what may have caused it was a failed translation of English units into metric units. So because someone went with imperial units and another person or another group went with English units, it caused this extremely expensive, long time coming probe to crash into Mars's atmosphere. So if you ever go to visit Mars, you might see remnants of it, provided they didn't all burn up. Now, a bit closer to home in Canada, another issue of unit conversion happened in 1983. You may have heard about this if you were alive at the time, but an Air Canada flight actually ran out of fuel over Gimli, Manitoba. Canada, having about over a decade before, switched to the metric system. So in 1970, Canada was on the metric system. However, it took a while for this to roll out. So Air Canada's first aircraft, which was this one, was the first to use metric measurements, and so that led to some confusion on the ground crew. And so when you need, say, 5,000 gallons of fuel, and someone only gives you 5,000 liters, you're going to have a really bad time. Thankfully, the pilots knew of an Air Force base that was nearby, and were able to land it safely with no deaths and no casualties. And so this plane was actually nicknamed the Gimli Glider. Now, there are just two more instances that I want to talk about. One quickly is an error in measurement from sea level. So, sea level is something that we think is universally defined, but actually varies from country to country. So in a place like Germany, sea level is based off the standard sea level, which is from the oceans of the world. Particularly, Germany is quite close to the Atlantic Ocean, so we can kind of use that, and also the North Sea as a reference. However, a place like Switzerland is closer to the Mediterranean Sea, which is just slightly higher, about 27 centimeters higher than the North Sea. And so if you define one country's sea level as being based on the North Sea and the other as being defined in the Mediterranean, you'll see that there's a difference of 27 centimeters. However, Switzerland and Germany share a border, and because of this mismeasurement, instead of counteracting those two and getting 0 centimeters, when they went to go build a bridge, they found that the Swiss side and the German side were 54 centimeters apart, so double that difference in sea level. So the bridge actually had to be adjusted and lowered before it could be connected. And this is something that's an issue, especially when you're building a bridge from one country to another. Now, there is, I guess, a smaller aside, just for not accounting for some measurements. So the Millennium Bridge, which is in London, it's a footbridge which is right outside of St. Paul's Cathedral, was built for the Millennium, and it's a 350-meter long bridge over the River Thames. Now, they designed it to take account for bouncing it, since it's kind of a suspended bridge, and with so many people walking across it, they accounted for the fact that it would bounce up and down with their steps. However, what they didn't account for was the side-to-side motion of this bridge as people were walking. And we got with this bridge what was known as a resonant frequency, where the frequency of the side-to-side movement of the bridge almost exactly matched the length of a person takes to take a step. And so, with that frequency, people would kind of adjust their steps as the bridge swayed, and so it would sway even more. And then more people would adjust their steps, and as more people walked on the bridge, it would sway more and more, to the point where they had to shut it down and relook at the calculations. So, it's really interesting to see how simple mistakes can lead to major problems, like almost crashing a plane in Canada, or actually crashing a very expensive orbiter in Mars. So always make sure to measure twice, cut once, and don't crash anything.
Yes. It will, unfortunately, those occurrences will probably not be the last time someone misconverts some units and causes a problem, but people learn from their mistakes, so hopefully it happens less and less and less. And that bridge is also, that whole bridge is like something you could talk about for an episode on its own. It's a very interesting engineering event and resonance event, and even like a sociology thing where like people all will step in sync because it's easier, and anyway, stuff like that. But yeah, thank you for that. It's always really interesting hearing about people making mistakes like that, because it makes me feel better about my mistakes. But yeah, so thanks for tuning in, and we'll see you all next time.
Take care.
Bye, everyone.